2016, I was part of the Saigal Lab, and my project is on electronically-controlled drug release, source spinal cord injury treatment. So spinal cord injury is damage to any part of the spinal cord. Around 288,000 people live with spinal cord injury yearly, and it's defined by two parts: the primary injury, which is the initial trauma, and the secondary injury, which is the inflammation, which is a person's reaction to the trauma. And so our current treatment options for spinal cord injury are early surgical decompressions, elevating blood pressures, and lastly systemic steroids, which we administer via an IV. And these are often very controversial because there are systemic side effects, such as pneumonia, sepsis, and GI bleeding. And this takes a toll on the whole body. So our goal of the Saigal Lab is to eliminate the systemic side effects and deliver the drugs locally. This will in turn cause lower overall doses, have a higher percentage of drugs to the target tissue, and avoid systemic side effects like I mentioned previously. And so in order to localize drug delivery, we have to be able to control the drug release so that it only localizes in a certain region. And so we use a conductive polymer called polypyrrole, and we oxidize the polypyrrole so that it has a positive charge, and the drug has a negative charge. And so when these charges attract one another, that is called drug doping. And the second step is drug release, where we reduce the polypyrrole, and that causes the polypyrrole to have a negative charge, and the negative charge of the drug and the polypyrrole repel one another, and this notion of repelling is the drug release. So this is an example of the experimental setup. It's a custom electrode setup, and we use a polycarbonate plate, and we sandwich those two together with a silicone-based polymer and an ITO slide. The ITO slide is just a conductive plate that we use to be able to allow the stimulation to occur. And then this yellow region here is the drug layer with polypyrrole with drug and NADPS. NADPS is a dopant, so it allows the drug to adhere to the polypyrrole surface. And then we put a PBS solution. PBS stands for phosphate buffered saline, and this is similar to the salinity of human tissue fluid, and so we're able to mimic that effect. And lastly, we do this with and without stimulation. Without stimulation, we just allow the PBS to passively collect the drug layer so that it's releasing into the PBS. And then with stimulation, we turn on the power source and apply a negative potential so that we're able to allow the drug to release into the PBS solution. Afterwards, the PBS solution is taken to an absorbance reader and chloride. So for experimental drugs, we use minocycline, which is an anti-inflammatory drug, and secondly, we use squipazine, which is a serotonin receptor agonist drug, and it's been known to assist with rehab post-operatively. So my experimental question is, how do varying levels of NADPS affect controlled drug release? And this is my data. We dissolve 4 mg per ml of minocycline in varying levels of NADPS. The y-axis is concentration per minocycline, and the x-axis is time per minute in minutes. And we did 4 minutes of passive stimulation and 6 minutes of electric stimulation, and so that's indicated by the gray region shown there. And the orange line is indicating the lowest level of NADPS, and so from that we can conclude that we need a certain amount of NADPS to maximize the controlled drug release. And then for the second experiment, we use quipazine. We dissolve 0.5 mg per ml of quipazine in varying levels of NADPS. And we did the same experiment that we did with minocycline. And so what we found here was that, again, there was a certain amount of NADPS that we needed to use in order to maximize the controlled drug release. And so, just to sum up, minimal levels of NADPS is needed to allow maximal maximum drug release. And colchicine, the release may change with higher initial concentration because we might have used too little concentration of colchicine, so towards the end there wasn't enough drug to be released. So our future work is to develop implants to put in the spinal cord directly so that we're able to localize drug delivery in a certain region of the spinal cord, and we're using polypropyl to develop that. And our further experiments are to explore the parameters of different drugs, such as what I did for my experiment, to optimize drug release. I want to acknowledge the UW Neurosurgery staff and the Saigal Lab and the grant that supported this amazing program. I'll take any questions. And that's me.